Oh, hello there. I was just having a drink of water from a beaker. Do you guys want help with this lab? Yeah? Okay, let me teach you a little something about humidity first. You guys know that the air has water in it, right? This is not my drink. This is very cold water, and it's been super humid today. What is all over the outside of this glass? Come on, you can see it. Yeah. What's all over the outside of the glass? Oh, is the glass leaking? No. You guys know this is condensation. Moisture in the air is sticking to the glass. But why? Why does that happen? Do you want to know? So you guys know about humidity, right? It feels so humid today. Oh, it's so sticky. Oh, it's so muggy. But what you're actually feeling is not the humidity itself. You're feeling the relative humidity. You're feeling not how much moisture is in the air, but how much moisture is in the air compared to how much moisture could be in the air. So let me show you with my little beaker here and a second beaker. So this beaker is basically full, right? Let's imagine that this beaker is a quantity of air at a certain temperature, right? It's a warm enough temperature that it can hold this much water. Now, colder air, smaller cup, can't hold as much. The same amount of moisture that's no problem in warm air, if that air cools down, there's too much moisture for the air to hold, and it starts spilling out. So, first of all, the fact that the warmer the air is, the more moisture it can hold, that's our first thing. But how it feels to us depends on how full the water is. So you can have cold air, full to the brim, as full as it can possibly be, and that feels pretty muggy. You could have technically, let's make it a little bit more obvious. You can have a larger beaker. You have warmer air that is holding roughly the same amount of water, but feels drastically different because the capacity to hold water is so much greater. So this is really only about half full, right? 50% of the water that could be in it is currently in it. We would experience this as about 50% relative humidity. Now, when you're cooling the air down, you're going to get to a tipping point, right? You're going to get to a point where the air is so cold, the cup is so small, that it just cannot hold anymore. And that's when you get condensation. That's when you get actual liquid water droplets in the air or stuck to things like cold surfaces. Because the air in this room right now is like 72 degrees, and it's holding the moisture that it can hold. When that 72-degree air touches this ice water, it cools down. Oh, it cools down so much it can no longer hold onto its water, and so the water vapor condenses as liquid droplets on the outside of the beaker. So what is this tipping point called when the air is as full as it possibly can be, when nothing else can fit? The temperature here in this condition, whatever size cup we want to represent a temperature of air, this is called the dew point temperature. The dew point temperature is the temperature that the air needs to be cooled down to in order for the moisture that exists in it to be at maximum capacity. So if there's a little bit of moisture in warm air, you need to cool that air down a lot. The dew point temperature is going to be very, very, very low. But if there is a lot of moisture in the air, you don't have to cool the air down very much for it to, if we imagine just like shrink, just Photoshop real life here, shrink the cup to get to the dew point temperature. Lower the temperature until the capacity to hold moisture means that the moisture that's there is saturating the air. Because if it's not saturated, it's unsaturated. But this temperature, if you cool it down, this is where all the magic is going to happen. Cool it down any farther than that, you can't. I mean, you could, of course, you can cool it down farther than that. But once you reach the dew point temperature, that's when you get condensation. And if you get enough condensation, you get precipitation as well. So how does that affect what does it have to do with the lab? All right, so this water that I've spilled everywhere, is it going to stay like this? No, it's going to evaporate eventually. Well, you guys know that if you put a pot of water on the stove, you have to add some energy to get it to boil to turn into water vapor. But do you have to add any energy to get water to just evaporate from liquid into water vapor? Technically, yes. The energy comes from the air itself. So as the air molecules have a certain temperature and the air molecules bump into the water molecules here, they give them some of their energy, and that eventually the water molecules collect enough energy in order to be able to evaporate into moisture in the air, and that leaves the air temperature a little bit cooler. Evaporation causes cooling. Don't believe me? You can try it out. Put some water on your skin and just feel. It will feel colder. That is actually why we sweat. Our bodies are trying to cool us down. We put some moisture on our own skin and it evaporates, and evaporation causes cooling. So here's where we're going to use this Sling Psychrometer. It's just 2 thermometers, and it's wet. So one thermometer is just a regular thermometer, right? We can use this to measure the air temperature. The other thermometer has a little wet piece of cotton on it, and it is wet. It is shouldn't be dripping. If you need to moisten yours, you can just drop it into a beaker or a puddle, and then squeeze it out so that it's not dripping, and slide it back over the thermometer. And here's why. We're going to spin this around a little bit to give all the air molecules a chance to do what they're going to do, to give the water on that little sock a chance to evaporate if it can. If the air is already almost full, there's going to be very slow, very little bit of evaporation off of this wet cotton on the wet thermometer. And so we're not going to see much of a wet bulb depression. It's not going to be that much lower than the regular dry thermometer. But if the air in the room is dry and therefore there's a lot more space, there's plenty of space for the water molecules that are on this little piece of cotton to evaporate, then a lot of evaporation can occur. And that means a lot of evaporative cooling can occur. And so our wet thermometer will be much cooler than the dry one. So as I've been spinning this for a few minutes, I can see that, the temperature has gone down. It is only 18 degrees Celsius in this classroom right now. That's the dry thermometer. When I read the wet thermometer, it is 15 degrees Celsius on the wet thermometer. So if we open up to page 12, I've got 2 charts. I've got one that I can use to determine the dew point, and I've got one that I can use to determine the relative humidity. They both work exactly the same way. They just give you different information. So make sure you're looking at the right one to get the right numbers that you need. We're gonna look down the side of this chart for the dry temperature. So what did I say it was? 18 degrees. Okay, so the number that I need to find for the dew point temperature in this room is going to be somewhere along here. How far over do we go? Well, I need to find the difference between the wet bulb and the dry bulb. This is called the wet bulb depression. How much lower was the wet bulb? How much evaporation was actually able to occur in the conditions we currently have in this room? So what did I say? It was 15 difference between 18 and 15, that's 3 degrees lower. So I go between 3 degrees lower and 18 degrees, and am I doing that right? 13. 13 degrees is the dew point temperature. To reduce the air temperature in this room to only 13 degrees Celsius, suddenly all of the moisture that's in the air would start to condense. It would condense on the desk. It would condense on the inside of the window. It would condense on me. Everything would feel wet and damp and sticky and nasty. And if it happened fast enough, I suppose, if there was a controlled air pressure in this room, it would actually even form fog, which is just a cloud on the ground, and maybe technically precipitation. Could we do that? I don't know if we could actually make that happen. Let's take a look at another number that looks a little bit more visible. So let's look at the relative humidity again. Same numbers. Okay, it was 18 degrees Celsius, and the wet bulb was 3 degrees cooler than that at 15 degrees. So 3 degrees cooler, 18. The relative humidity in this room is 72%. 72% humidity. But here's the thing, remember, the capacity of the air depends on the temperature. In fact, we've got this chart here. At a certain temperature, this much moisture could be held in that air. So at about room temperature, the normal amount, let's see, room temperature would be about, it would be about 20 degrees. The amount of moisture that could hold is 17.3 grams for every cubic meter. And a cubic meter looks like that, right? If we had like an amount of air that big at that temperature, it would hold that much moisture. But we can't feel that. All we feel is how much is there compared to how much could be there. Okay, so as you're doing this lab, you're going to grab a Sling psychrometer. There are good ones, and there are kind of crappy ones that work just fine, that have just two, they're stuck together. 2 thermometers just on a string. Okay, it doesn't matter which one you use. You're going to either get the little cotton sock off of the back of it and get it wet, or you're going to get the little tissue taped to the bottom of one of them wet. You're going to spin it around. For like a minute. You don't want the thermometer to read the temperature of the water you put on it. Like if you use hot water or like ice water, it's going to throw things off. You want it to be just wet, just damp. Like give it time for the thermometers to adjust. And then read your dry thermometer, read your wet thermometer, and check your reference table. You're going to do this inside and outside. Hang on a second. I am outside. It's still Wednesday. What's happening on Wednesday? It's raining. I mean, it's like kind of raining. It was raining harder earlier, but like it's bleh weather. You want to guess what the relative humidity is? You want to guess what the dew point temperature is right now outside? How much lower do you think the temperature needs to go before moisture starts falling out of the air like it's doing already? You probably could put 2 and 2 together already, but if there's already precipitation, that means we are already at capacity. We are at the dew point temperature. We have cooled the air enough that the air can no longer hold moisture and it's falling from the sky. And if we check the dry thermometer temperature and, what does that say, 14, and the wet thermometer temperature, it's hard to see. Okay, so it's technically time, but let me spin it a little bit longer. I haven't been out here long enough. But it should be the same, right? It should be the same temperature because if the moisture capacity of the air is already, too, what am I saying? You get what I'm saying. I'm tired. It's time for me to go home. You guys are going to be able to do this lab easily without me. Help each other out. If any of you are good at doing this, you can get numbers easily. Please check next to the chicken eggs. We need to know what is the moisture like around those incubators, because the inside of those incubators has to have a specific relative humidity in order for the eggs to be healthy. So somebody please do that for me. Thanks. Bye.